This lecture focuses on possible ways variables can relate to each other. The lecture is based on slides prepared by Dr. Lin and modified by Dr. Alemi. It is also based on the treatment of the topic by Alan Agresti in the book on categorical data analysis, narrated by Ariane Maslon. We say that two variables are independent from each other when knowing the information about one variable does not tell us much about the other. For example, the diseases of two patients may be independent when knowing that one patient is sick does not tell us much about the likelihood of the other being sick. Of course, this is not the case when the disease is infectious or if the two patients are related or if they ate the same food. This concept is relatively simple if we are thinking of two variables. Then the probability of event B given A, that is the probability of B given that we know A has occurred, is the same as the probability of B. In essence, knowing A does not change the probability of B. Another way of saying this is that if we shrink the universe of possible events to all situations where A has occurred, then still B has the same probability. A is a subset of the possible events, and since B is conditioned on A, then we can select all events that A has occurred and ignore the rest. Suppose in this table we are looking for probability of B given A. This table shows a contingency table in which count of various combinations of event A and B is given. The total sample size is A plus B plus C plus D. By definition, the probability of any event in a sample is the number of times the event occurs divided by the size of the sample. The probability of an event A is the number of times A occurs divided by the sample size. The real question is what is the probability of B given A? We can take the concept of conditional probability as recalculating the probability of the event, but now in a smaller sample where the possible causes are limited to all cases that meet the condition. The first step is that we shrink the sample size to the situation where the condition is met. The condition is that event A has occurred. So now the sample shrinks to only cases where A has occurred. All other events are no longer possible and therefore not part of the sample. There are A plus C cases where event A has occurred. This is now the new sample of the possible events. We want to know the frequency of event B among these possible cases. We had earlier defined probability as the frequency of an event among the possible events. We note that event B occurs A times, so the probability of B can be calculated as its frequency divided by the new possible events, which is now A plus C. Thus, we get to measure a conditional probability by restricting the sample to available cases and examining the frequency of the event in the new table. Similarly, we can calculate the probability of A given B by reducing the sample size to all situations where B has occurred. This reduces the cases to A plus B. The probability of event A given event B is then given by number of times event A occurs in the new smaller sample size divided by the size of the new sample. Or another way that may appeal to those of you who know SQL, if for binary variables A and B, we restrict the data to only cases where A has occurred, then the two calculated probabilities for B should be the same. Let us use what we just learned about how conditional probabilities can be calculated in a sample of cases. Here, we have two events and the count of their co-occurrences. To estimate probability of A given B, we need to shrink the data to the situations that B has occurred and then calculate the probability of A in the reduced sample size. For example, knowing that patient A has a heart attack does not change the fact that the next patient who comes to the ER has a heart attack. This is probably a reasonable assumption if the current and the next patient are not related or do not influence each other's lifestyle. Note that for independence to hold, it must hold at every level of A. It should be true that when A is present, it should also be true when A is absent. So to say with our earlier example, then knowing that the current patient does not have MI or heart attack does not change the probability that the next patient will have MI. The two events are independent, and independence holds for both when the condition is present or absent. We typically do not show the absence as dealing with negatives is cumbersome, but whether we show it or not, you should always keep it in mind. Here is another example. Suppose we have two clinics, one in San Francisco and the other in District of Columbia. If I tell you that lots of people are waiting for service in DC, it may not change the probability of people waiting in San Francisco. It would if there was a national demand for our clinical service. But in absence of this national demand, we are safe to assume that the two clinics' waiting times are independent. As we had also said before, this relationship holds for whether the wait time is long or short in DC. The independence of two variables can be shown as a function I, taking two parameters of A and B separated by comma. Sometimes I is dropped, and only the two variables are shown with comma separating them. Graphically, this is shown as two variables without a link between them. If a line is shown between the two events, then the relationship exists between the two events. They are correlated events. So here, A and B are related events, and knowing something about A changes probability of B. If a direct line is shown between the two events, then a causal relationship is assumed. This graph, for example, says that A causes B. If two events are independent, then neither a causal or an association relationship may exist between them. Of course, sampling data creates random variation, and two samples, no matter how independent, may not exactly have the same probabilities. Chi-square tests allow us to examine if the probability of two events are related. Each observation is compared to the expected value of the observation under assumption of independence. There are published tables that give the probability of observing different values of chi-square test statistic. This allows us to decide if two variables are independent even if there are small changes in the probability of one event given another. But if we are dealing with three or more variables, the situation becomes complex. Now all variables could be independent of each other, or pairs of variables can be independent, as well as other possibilities arise. There are 5 unique ways 3 variables could be related to each other, and scientists have named these ways. These 5 unique ways are called complete independence, joint independence, conditional independence, homogeneous association, and saturated models. In complete independence, all variables are independent of each other. Here we are showing the 3 variables A, B, and C without any linkage between them to mark that they are independent from each other. Joint independence is the situation where 2 variables are independent of a third. In these graphs, a bar between 2 variables indicates that they are dependent on each other. In other words, there is a relationship among them. There are three ways joint independence could occur among three variables. AB could be related but independent of C, AC could be related but independent of B, and BC could be related to each other but independent of A. Conditional independence refers to the situation where knowledge of one variable is sufficient to make two previously dependent variables independent. A directional bar indicates that they are only dependent on each other when information about the other variable is known. There are three ways conditional independence could occur. Knowing B could make A and C independent. Knowing C could make A and B independent. And finally, knowing A could make B and C independent. This is the situation where each pair is jointly independent from the third variable while holding the third variable at various fixed levels. Another way of saying this is that the presence of a shared feature of a variable does not change the relationship among the other two variables. Thus, the relationship between A and B remain the same independent of the shared feature of C. Finally, saturated model is the situation where all variables are dependent on each other. These models are arranged in order of parsimony, with complete independence being most parsimonious and saturated model being the least parsimonious. In science, when a more parsimonious model fits the data, then it is preferred to the less parsimonious model. So if data can be modeled with both saturated and conditional independence, then conditional model is preferred. If data are completely independent, then these data can also be modeled by any of the other 5 methods, but preference is given to the complete independence model. The remainder of this lecture focuses on possible ways these different types of independence can be recognized. The general approach is to use the model of the data to estimate the count of data that should be expected in each cell in the table. Then the difference of the observed and expect values should be distributed using a chi-square distribution, and we can test if the model fits the data. In each instance, we provide a model for estimating the expected count and the degrees of freedom for the chi-square test. Degrees of freedom is estimated as the number of observations minus the number of parameters estimated from the data by model. Chi-square test of independence merely indicates the degrees of evidence of association. These are inadequate for answering all questions about the dataset. Rather than relying solely on the result of the dataset, one must investigate the nature of the association, study residuals, decompose chi-square into components, and estimate parameters such as odds ratio that describe the strengths of the association. Suppose that we have 3 categorical variables, A, B, and C, where A takes possible value 1 through I, B takes possible value 1 through J, and C takes possible value 1 through K. For example, A could be 2 physicians in our clinic, George and Smith. B could be 2 nurses in our clinic, Jim and Jill. And C could be whether a patient has complained about the combined physician-nurse team. It takes on values of yes and no. If we collect the triplet A, B, and C for each unit in the sample of n units, then the data can be summarized as a 3-dimensional table. Let Y be the count of the units having A being I, B being J, and C being K. Then Y will provide a count for each cell in the new 3-dimensional table of A, B, and C. When all variables are categorical, a multidimensional contingency table can be displayed. For example, Y is the count of patients who were seen by clinical team George and Jill, and who had complained. This is one cell value in a larger table. Each cell in this table is one of the observed counts. In this table, we see the distribution of Y for different clinical teams and complaint combinations. We see the distribution of the counts for different combinations of A, B, and C. In the last two rows and in yellow, we see a marginal table for the count of complaints for just nurses, ignoring the physicians. Note that a marginal table is the total of values while removing one of the variables. The cross-sections are called partial tables. In a partial table, one of the variables are held constant. For example, in a partial table shown in yellow, the value of physicians is held constant to always be George. All of the data in this partial table are about teams involving George. We will use plus sign to indicate summation over subscript. For example, here we are summing over the subscript j to produce a marginal table involving subscripts I and k. In this marginal table, variable b is ignored. Note that we drop the comma between the subscripts to save space. Here both the subscripts I and j are summed over. We are ignoring both the variables a and b. We see count associated with k levels in variable c. This is equivalent to totals for a marginal table of variable c. If the n observations in the sample are independent and identically distributed, then the vector of cells counts y has multinomial distribution. Note that y and the symbol pi are in bold. These constructs are vectors or collection of variables and not a single variable. We are assuming across patients that have independent and identical distributed variables. This seems appropriate in many situations where the data are obtained from different patients and where there is no reason to believe that value of one patient can affect value of another. This assumption is not met when patients have infectious disease, as the probability of infection of one patient is affected with the infection of another. It is not valid when over data collection time the underlying process has changed. Under the multinomial assumption, estimated probabilities for a cell is calculated by dividing the count in each cell by the total number of patients. Because this probability is estimated from the data, we show it with a hat on top of the p to emphasize that this is an estimate and not the observed value. Note that the expected counts for each cell are equal to the observed counts. Multiplying the sample size by the estimated probability of the cell gives us the expected count, which is the same as the observed count. These expected counts can be used in the chi-square test to check if the model fits the data well. The first model we show how to test is the saturated model. The observed sample proportions and by extension observed sample count of each cell is often called the saturated model. In the saturated model, the expected value for each cell is used to complete the chi-square test. Fitting a saturated model might not reveal the special structure that may exist in the relationships among A, B, and C. To investigate these relationships, we will propose a simpler model and perform tests to see whether these simpler models fit the data. If one of the variables is being predicted, then the saturated model can be thought of a logistic regression of C on the main effects of A and B, as well as the interaction of A and B. The model of homogeneous association says that the conditional relationship between any pair of variable given the third one is the same at each level of the third one. That is, there are no interactions. An interaction means that the relationship between two variables changes across the level of the third. This is similar in spirit to a multivariate normal distribution for continuous variables, which say that the conditional correlation between any two variables given a third is the same for all values of the third. Under the model of homogeneous association, there are no closed form estimate for the cell probabilities. In the 2x2 partial tables, the odds ratio can be calculated, and a chi-square test of homogeneity can be carried out. The degrees of freedom for this test is I minus 1, if I is the number of levels of the fixed variable. The procedure needs to be repeated holding the other variables fixed and examining homogeneity of the odds across the level of the other two variables. In addition, to effectively implement the procedure, data needs to be expressed in 2x2 tables. If it is not possible to calculate the variance because one or more of the cell values are 0, a method to estimate the chi-square statistic that bypasses division by 0 is provided by these formulas. First, the data are organized into L strata, each strata being a combination of two variables. The probability of the outcome in the L strata is estimated. Then the expected number of cases in each of the L strata is estimated. The observed and expected values are used to estimate chi-square with L-1 degrees of freedom. In 1949, Lancaster showed how multi-level variable can be divided into 2x2 tables and tested using chi-square. Each of these partial 2x2 tables must have the same homogeneous odds. This model indicates that A and B are related. A and C are also related, but only through their mutual association with A. For a given level of A, then B and C are independent. If A is used to stratify the data, then within the strata, B and C are independent. The test for conditional independence of B and C given A is equivalent to separating the table by levels of A going from 1 through I and testing for independence within each level. This model indicates that A and B are related, but C is independent of these two. The model is tested by creating marginal tables and using the count in these tables to estimate the count in the I by j by k cells of the observed data. A chi-squared test can be used to test this model. Note that in three-variable models, one can test the joint independence of AB, AC, and BC from their complements. Here we are showing how to test if AB is independent of C. Under the assumption of complete independence, the joint count can be estimated from the product of the marginal counts. Then the square of the differences of observed and expected count has the chi-squared distribution, which can be tested using the corresponding degrees of freedom. This table is a 2x2x2 contingency table, 2 rows, 2 columns, and 2 layers. In this table we see how 2 physicians are working with 2 nurses and whether their patients have complained. The data is hypothetical, but it is easily available in complaint registries within most hospitals. The 684 patients classified in table were patients at this hypothetical clinic. We will use this table to estimate the relationship among the three variables. We used the formula to predict the counts within each cell and then calculated the chi-square with 4 degrees of freedom. The chi-square statistic is 49.33, which is statistically significant, and therefore the complete independence model does not fit the data. Using the test of joint independence, we find that assuming that A and B are related and independent of C produces a chi-square of 0.52, which is not statistically significant, at 2 degrees of freedom. Therefore, we cannot reject the hypothesis that the model fits the data. The model assumes that the impact of the clinical team depends on who is working together. The combination of the team matters. It is interesting that the model fits the data well, as it tells us that the team composition matters. Other tests can be carried out in the same fashion, each time calculating the chi-square. Since we wish to rely on the most parsimonious model, we have already found a very low chi-square. Therefore, we can stop here. You may wish to carry out the remaining tests to see if there's also additional insight into the structure of the data. This lecture has shown how various tests can be carried out to get insight into the relationship among three variables. Each test provides new insight into the data.